Thanks, Rob. So I came in 2008. But I guess I was in the lab. Maybe you didn't notice in 2008, because I was in the lab pretty much all the time that year. So maybe it didn't seem like I appeared till 2009. So that means I've been here 6 years. So I'm only an order of magnitude away from catching up with Jim Dye. So I look forward to trying to match that, but I don't have that high of hopes. So I guess I first want to tell you about what motivates my research interests. I'll talk about some of the research that my group is working on and has been working on over the last 6 years. But I really have to say a lot of what we're working on are things, at least concepts of what I started when I was applying to graduate school. And I knew when I got to graduate school, it was going to be a lot of hard work. And I was ready to work hard. But I really wanted to work hard on something that I thought was a really important topic. And so then I started to think about what are the really important problems in the world. And well, this is a recent report, but this is when I started to think about alternative energy, research in alternative energy, because it was already known, I don't know how long that was, 15 years ago when I was applying to graduate school, now that the world's population was growing and the populated parts of the world are industrializing, and that's good, and this is causing a huge increase in the demand for energy, and that's going to increase. And then you worry about what are the consequences of this. I mean, certainly I want the world to develop and industrialize, and this is going to require a lot of energy. And so then where does that energy come from? And it comes from fossil fuels, and then it's a concern about what happens, what are the environmental consequences of continued burning fossil fuels. So that's really what I thought was the big problem, and every other problem of supplying the world with food and water and education. These are all linked in health, and these are all linked with energy, right? You can't have increases in technology without increasing our supply of energy. So and this is personal. I'm actually not worried about the environmental consequences for me in my life. I think we're going to be fine, but it becomes personal now when I think about the world that my son, he's only 2 now, but he's already a Spartan fan, as you can see. That's his favorite shirt. So I just think about the world that he's gonna live in now. So this is something that I still think about. It still motivates me, and I still think energy is the most important problem for scientists to work on. And at least that's what I'm going to work on. So if we don't continue down the path of burning fossil fuels, then you have to think, well, what else are we going to do? Where do we get our energy from? And really, there's only one answer that makes sense, and that's solar energy. And that's really just because of the abundance. There's more solar energy, more energy from sunlight hitting the Earth than all other resources combined. It far outweighs all fossil fuels and wind and nuclear power that's available. Maybe not nuclear, but that's another day, another topic. Okay. So then we actually know how to harvest solar energy pretty efficiently already. This has been around for decades. And the problem is really one of cost. My wife tells me that we can't afford to put solar panels on our roof, and I believe her. And that means if we can't afford it, then I can't expect people in India and China and Africa to try to buy solar panels rather than burn coal, which is just what makes sense, right? So we have to make that answer very easy for them and sort of resolve the problem of can we provide cheap solar energy that's also efficient and scalable. So it has to be scalable to meet the world's demands, not just our demands. And then that becomes a really hard problem. And so one of the systems that we're interested in is a dye-sensitized solar cell. And the reason is because its substrate is, well, they're very easy to make. It's essentially white paint. And it's hard to beat in terms of cost effectiveness, just white paint, painting on a piece of glass. You heat it up and you soak it in dye and squish it together with another piece of glass and you have a solar cell. And that's what they look like when we make them in our lab. And well, they're starting to come into the marketplace. These are dye-sensitized solar cells, so you can soak them in different dyes, make them different colors, so they look quite nice. But they're not that efficient. And so therefore, this is the science problem that we want to work on. What limits the efficiency? What understanding gaps are there that we can address and then allow us to sort of design the next generation of solar cell that's going to be cheap and efficient and scalable and all these requirements that are really necessary if you're going to make a dent in the world's energy picture. So this really becomes a materials problem then. So this is sort of a schematic. It's a little bit complicated. I'm not going to walk you through that. But I will tell you about a couple of the things that we have found in the last couple of years. And that is shown here in the yellow. I don't have a laser pointer. These are electrons. We've been able to sort of separate, as a consequence of having this as a cheap material, that it's white paint, you have a lot of defects. It's not like the really pristine silicon solar cells that you currently can buy. And these defects are in trapped states. And this can be a problem. So we've been able to characterize the fraction of electrons that are in trapped states versus the ones that are free and mobile in the conduction band. We've been able to separate the behavior because they actually have very distinct behaviors in recombination. So in general, in a solar cell, you want to absorb light, and you create electrons in holes. And then you have to move them, separate them, and collect them at different electrodes, and that makes a power, a solar power, right? And so then you're always fighting against those charges coming back and recombining. That's general for every solar energy conversion system. And so in this case, the recombination mechanism is interfacial electron transfer. And so that's what we spent the bulk of our time trying to understand the details of that, how electrons go back from the white paint or these nanoparticle TiO2 materials, and they go back into solution. Okay. And we've also struggled, and I think we've been recently successful with trying to solve what seems like it should have been a solvable problem, but it hasn't been solved for the last 20 years, is trying to understand where the energetics map out the energy of a conduction band in a nanoscopic material. And there really was no method to do that. So one of the things we've gotten interested in, just because we have to map out the energetics if we want to understand, get a good physical picture of how things work. So we've developed a methodology to monitor the absorption of free electrons and separate that out from trapped electrons and monitor that as a function of temperature, applied potential, and correlate that with a decrease in absorption here. And this has allowed us to quantify the actual absolute conduction band energy for the first time, I think. Okay. And so now this is starting to give us some design rules and saying we understand, I think, in a lot of detail of how a dye-sensitized solar cell works. We understand the limitations. We have a good picture. And so now we're using this to start to develop sort of the next generation of dye-sensitized solar cell. And I think that's where we're headed over the next 5 to 10 years, hopefully 5, actually, but we'll see. So there's another big problem with solar energy conversion, and that a lot of you have probably noticed that at night the sun goes down, and then that tends to be a problem because then you can't power things if you're relying on sunlight. So we have to find a way to store solar energy. And as Rob pointed out, I grew up in Alaska, and then the sun goes down for half the year. And, well, we don't want to live without electricity for half a year. And so we've been working on ways to store that in chemical bonds. So this is a prototypical example of using sunlight and trying to concentrate it and store it in chemical bonds. So driving chemical reactions with solar energy. And this is a prototypical example of splitting water. And then you evolve oxygen and hydrogen. And now you can use hydrogen if you were able to store that, use it in a hydrogen fuel cell, for example. And so now you really just need sun and water. And if you can do this conversion efficiently, you're set to go, basically. Okay. So this is sort of a diagram. We've been looking at iron oxide as our model system. And you absorb light, right? We make an excited electron in a hole. And then we need to separate those. But there are lots of mechanisms that are fighting against being able to separate and collect these charges. And those are shown here in red. And then once you get charges to the interface, you have to collect those and do the right chemical reaction versus recombining or doing some other reaction that you're not interested in. And so these are all, we've systematically gone through one by one. How does the back interface, how does that control the ability to separate charges and collect them? How do the bulk properties affect it? How the surface, which turns out to be the most important thing, is the water oxidation reaction on the electrode surface. How do all of these ultimately affect our ability to efficiently take sunlight and split water with that? So we've kind of gone through systematically step by step and looked at each of these reactions and tried to find what is the rate limiting step, and then using that to devise strategies to sort of overcome that through material synthesis strategies, addition of catalyst. And so this is actually, I can show now quantitatively our progress. This is one of representative in the red curve of one of the first JV curves we took in my second year. So current voltage curves is a measure of the efficiency of the system. So the larger current at a certain voltage, so the more the curve is that way, the higher the efficiency. And now we've systematically marched from this red curve, which looks terrible if you ever look at if you're ever familiar with photovoltaics, up to the purple curve, which is now, I think now we're the best in the world at making hematite photoelectrochemical cells. And that's really been a sort of a long systematic march towards improvement. So we still have a long ways to go, but I like the methodology that we've developed, and I'm still excited about seeing how far we can push this. So a third topic we work on in my group, and this is really inspired by my colleague Mitch Smith, which it took me a couple of years probably to really catch on and get excited about it, but now it's something I'm very excited about, and that is in the chemistry of ammonia. So that actually starts to bring us back to some of Jim Dye's early work on looking at liquid ammonia. So now we started to work in liquid ammonia, and the idea is, well, there are two reasons why you want to look at ammonia. One is hydrogen. If we are successful at using sunlight to split water and you're making hydrogen gas is not that easy to store. It's not that easy to transport around the country, but ammonia is. So if we can take sun and air and water, and with the right catalyst, you can convert that to ammonia. And now not only do you have a way to store solar energy, you also have a way to make fertilizer. Right? So this is a way to use renewable energy sources like wind or sun power, make ammonia on site, and use that to fertilize and increase the ability to farm around the world. Okay. Of course, if we were successful in this, now we have to find a way to get the energy of ammonia back out. So we have to, there are two ways to do that really, is to do a direct conversion of ammonia to energy, or we can split that back, get the hydrogen back out, and use that to power a fuel cell car. And Toyota has recently, this year, they're rolling out with commercial hydrogen fuel cell vehicles. So I think that this actually has a chance of catching on in the future, whether it's hydrogen or whether it's ammonia. I'm not sure. That's, I guess, our challenge to try to solve these problems. So this is our first example of doing electrolysis of liquid ammonia. We have a long way to go, but I think this is the second example. There's one example in the literature. We're slightly better than them. I think we've sort of worked out what the actual reactions are happening at the electrodes, and now this is giving us hopefully the insight to develop new catalysts. And I think this is the direction that my research is going to go in the future, is really all the action happens at the electrode interface. So it's heterogeneous catalysis and looking at chemical reactions at electrode surfaces that is going to be a big part of my research over the next, well, decade. It's hard to see further out than a couple of years, but let's say decades. Okay. So those are the three main areas, all under the guise of solar energy conversion in some aspect. And of course, I'd like to thank, well, first my colleagues up there. It's the colleagues and the people at Michigan State who make it a lot of fun and also really exciting to work there. And these are my first two students who were brave enough to join my group when I came to Michigan State. They got here the same time I did. Ben and Jesse. Ben is not a very good sailor, but a very good chemist, which turns out to be more important. And of course, not only my colleagues, but my students, not the first two students, but this is a recent picture of my group and all the students and postdocs who've done the work that I've showed you. And of course, Laura for agreeing to marry me and move to Michigan, and our son, Max, who provides daily inspiration. And that, he's still wearing his Spartan shirt, notice, and that's not on the same day or planned. That's just how it comes out. And yeah, thank you for this honor and your attention.